In class today, there was a question about how one goes from, let me put here in color white, how one goes from the ideal gas model. And remember the ideal gas model, gas particles have mass but zero volume, and they engage in elastic collisions with the wall of the container, and there's no interaction between gas particles. With that model, how does one arrive at the fact that the kinetic energy is 3/2 RT? How does one go from that to that? All right, this is interesting. Just let me wax philosophically here for a minute. Temperature is a macroscopic variable. In other words, temperature. You talk about, you put a thermometer in a water bath and you measure its temperature. It's macroscopic. Kinetic energy over here, this is microscopic. So microscopic, and the idea is you have, atomic molecular theory and kinetic molecular theory. So what you do is you get the kinetic energy of these gas particles, these microscopic gas particles, and relate them to a macroscopic quantity. And in fact, that's often what physical chemists do. They have some model, which is a molecular model, and from that they try to predict the results of experiments in which typically you measure macroscopic quantities. Okay, so let's start out by having a one-dimensional box, and say this box has a length L. And it's just one dimension. Let's call this the x direction, back and forth. So what you have are gas molecules bouncing off the walls of the container. They're going back and forth here, boing, 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 like the old game Pong. You're probably too young to remember what the old game of Pong was. So we'll just go back and forth, and in one dimension. All right, so let's take a gas molecule, and it goes this way. It collides with the wall of the container and bounces it right back again. There's no energy loss. These are elastic collisions. So where are we going? This is a molecular picture, and what we want to do is to relate it to a macroscopic quantity. So eventually you want to have macroscopic variables like pressure, temperature, and volume. And that's what we're going to do. All right, so let's look at the momentum of the gas particle. Well, momentum really is a vector quantity, so I have to make a momentum of the gas particle. It's moving in the x direction with some velocity vx, and it has some mass m. Mass times velocity. The velocity here is the vector. All right, so there's the momentum of the gas particle moving along this direction. Let's, instead of looking at vectors, let's look at the scalar quantity here. This would be mass times the speed in the x direction, velocity in the x direction. So this has a certain velocity going here, and let's call this before collision. It's going along in this direction. After the collision, the molecule bounces back this way. So the momentum of the gas after the collision is minus m times the velocity in the x direction. It's going the opposite direction. This is after collision. All right, so that the change in the momentum of the gas particle is final minus initial minus 2 times the mass times the velocity in the x direction. All right, so what is happening when this molecule transfers momentum to the sides of the container? What's happening is that you're generating what's known as a pressure. So that's why pressure arises in the ideal gas model. Molecules are colliding with the walls of the container, transferring momentum, and that gives rise to a pressure. All right, so let's look at pressure now. Pressure, and let me use this capital P. Don't confuse this with momentum. Is defined as the force per unit area. Okay, so this is pressure now. This is a force per unit area. We know that force, from Newton's second law, is mass times acceleration. And let me write this as the mass times how velocity changes delta with time. Okay. Let's assume we're in a non-relativistic system, so that mass is a constant. As you know from Einstein's theory of relativity, mass changes if you approach the speed of light. So this will be, we'll put the m inside of there. So this is how the quantity mv changes with time. And again, it's the velocity in the x direction. And this is how the this is then momentum, which I'll use a lowercase p. Hard to tell the difference. All right, momentum in the x direction. Let's go back up here. So this is p gas. So the change in the gas momentum is minus 2mv, but it transferred that momentum to the sides of the container. So the pressure, the change in momentum in terms of the gas container wall is plus 2mv. Okay, so this is just equal to, it's equal to how, say, pressure in the x direction changes with time, and that's equal to plus 2 times the mass times the velocity in the x direction divided by delta t. So that's what the force is. And why we're doing pressure? Well, we want to relate this to a macroscopic quantity, and now here we have microscopic quantities, mass of gas particles and their velocity. Now, what is this delta t? Delta t is the, in this model, again, it's a model. Delta t, hello? Well, clearly I've done something wrong. Let's go back up here. There we go, the ideal gas model. Delta t is the time between collisions. So it collides here. Let's start here. It goes all the way here, collides with this wall. It's one dimension, comes right back. So the distance that the molecule has to travel is L, capital L, the length of the box, times 2. Let's go one length, then another, before it hits there. So the total distance. So delta t, the time between collisions, we equal the 2 times the length of the box, that's how far it has to travel, divided by the velocity in the x direction. Okay, so that's the time between collisions. We substitute that right in there, and let's now get an expression for force. Force is equal to, what did we say, 2 times the mass times the velocity in the x direction divided by 2 times the length of the box divided by the velocity in the x direction. All right, and we'll simplify this a little bit. This will just be m v in the x direction squared divided by the length of the box. The 2's cancel out, the vx comes squared, and that's the length of the box. We'll go back here. The definition of pressure is force per unit area, and we know what the force is. That's the mass times the velocity in the x direction divided by L times A. I want to convince you that this quantity here is V, or volume, of the gas. So this has the length as units of distance, and this is distance squared. So you multiply these two together, you get a volume. So this is equal to the mass times the velocity in the x direction, that should have been squared, divided by the volume of the box. Or, look at this, let's multiply, put the volume over there, pressure times volume is equal to m times v in the x direction, that's a v, not volume, and let's say multiply by 2 and divide by 2, mv in the x direction. Oh, what's this? 1/2 mv squared is kinetic energy in the x direction. So this is just equal to 2 times the kinetic energy in the x direction. So there we have it. Some macroscopic quantities are predicted from microscopic quantities, kinetic energy gas molecules in the x direction. All right, so this is for a single gas molecule, kinetic energy of a single gas molecule. Now let's look at a collection of, say, n molecules. So PV for N molecules, not quite, here we go. PV for N molecules, and a little trouble with this here. PV for N molecules is equal to N times the average kinetic energy times 2. Just make sure I got that correct. Yes, 2 kinetic energy in x direction. So this is the average kinetic energy in the x direction. So what I mean by average kinetic energy, the kinetic energy in the x direction, that's the average, will be 1/2 times the mass times the velocity in the x direction squared averaged. So you average the square of the velocities, and this is called the mean square velocity. So that's a kinetic energy. And this is for a collection of N gas molecules. Now let's remove the restriction. We had the restriction 1 gas molecule. Now we have a lot of gas molecules. Let's remove the restriction on x, just 1 dimension. And now extrapolate to 3 dimensions. So I claim the kinetic energy, average kinetic in 3 dimensions, is equal to the kinetic energy in the x direction plus the kinetic energy in the y direction, average, plus the kinetic energy in the z direction, average. I'm further going to claim that these are all equal. In other words, there's no preferred direction. If you go in the x, the y, or the z direction, you have the same kinetic energy. So this means that the average kinetic energy in a 3-dimensional box is just 3 times the average kinetic energy in the x direction, or the kinetic energy in the x direction is just equal to 1/3 times the average kinetic energy. So let's go ahead and do this for 3 dimensions, for 3D. We'll have this again as the PV in a 3-dimensional box is equal to the number of molecules times 2/3 times the kinetic energy. All right, so there we have it. That's an important equation here. It relates some macroscopic quantities to microscopic quantities. This is average kinetic energy in 3D. Now what we do is to insert here an experimental finding, that is the ideal gas law. So PV is equal to nRT. This is experimental. So if you take a gas and go to low temperature and look at gases like helium and argon that don't have any intermolecular interactions, what you find is essentially Boyle's law and Charles' law and Avogadro's law. Remember those from Intro Chem? From there you can get the ideal gas law. So look at this. PV equals 2/3 N, number of molecules times the average kinetic energy. And PV is also equal to nRT. Oh, that's kind of cool. So let's, just to make things simple, let's look at 1 mole of gas. So PV for 1 mole of gas is 2/3 times the average kinetic energy. So this is for 1 mole. And that's equal to RT for 1 mole. So these now are molar quantities. R is per mole and kinetic energy is per mole. Or in other words, the kinetic energy in the ideal gas molecule is 3/2 RT. There we go. So that's how one gets this equation that we put up in class. And the ramifications of this, okay, what you have are gas molecules. They're moving around in a 3-dimensional container. They're not interacting at all. Even though they have some mass, they don't see each other, so they don't interact. They're only bouncing off the walls of the container. They're not bumping into each other either because they have 0 volume. And so these molecules, and that's the molecular picture. From that, you can relate the average kinetic energy of these molecules bumping around in here on the sides of the container to 3/2 RT for a mole of gas molecules. Furthermore, this is an ideal gas, and the only way that the only energy that this ideal gas has is kinetic energy. There's no vibrational energy, there's no energy of interaction between it and itself or it and the walls of the container. There's just no other way for it to have any energy except for translational kinetic energy. That's the only way you can get energy. And that's the only way you can get energy. It only depends on temperature. Temperature is the sole determinant of the kinetic energy, and therefore temperature is the sole determinant of the energy of an ideal gas. So this implies that the energy of an ideal gas depends only on temperature, or expressed more elegantly, how U changes with temperature is equal to, how U changes temperature is, say, not equal to 0, or how U changes with volume is equal to 0. In other words, it depends only on temperature, doesn't depend on volume. All right, so I hope that clears things up. See you tonight at discussion.